In dealing with nonlinear scalar functions, we found it very useful to be able to do linearization, both for algorithms and for analysis. So now that we're dealing with multiple variables and multiple values in these functions, we want to generalize that linearization to the multidimensional case. So here again is the linearization of a function, just a function of one variable f of x, and the linearization is defined around a point A. So f of x is approximately f of a plus f prime of a times x minus a. So this part here is what we would call the linearization of f, or the linear approximation to f, near the point A. So now we're going to have capital F, that's a map from n variables to n values. Remember, we write that using this notation of Rn maps to Rn. So that means that x in this equation for the linearization is a vector, and the point, right, that we evaluate the linearization at is also a vector. So, naturally we can take little f and capitalize it, generalize it to capital F of x. And then on the right side of the equation, little f of a becomes capital F of a. And then the f prime of a becomes something. And maybe we can just leave the x minus a there, by analogy. So this thing here, whatever it is, right, it's got a vector sitting there to the right of it. And it has to have a vector value. So it has to map n vectors to n vectors. And the whole idea is for this to be a linear equation, a linear function. So this is going to have to be a linear map. Well, a linear map that maps vectors to vectors is a matrix. And that matrix has a name. It's called the Jacobian matrix of the function. So it's a matrix of all the possible partial derivatives. So remember, we can write the input variable x has components x1 through xn. And what we're doing here is we're writing the output, capital F, in the same way. So if we like, we could also write these things in terms of all the variables at once without using our vector abbreviations. And so you see this is actually a pretty familiar situation from vector calculus. Each one is a function of multiple variables, so we can take partial derivatives of each one of those functions. So in the matrix J, the Jacobian, sometimes we write this just as the matrix of df sub I dx sub j. In other words, the row tells you which output function, and the column tells you which variable. So the rows correspond to outputs, and the columns correspond to variables, or inputs, to the function capital F. One thing to note, just like when you first learned about derivatives, you learned that the derivative is itself a function, right? I'm trying to create a little room here. So in the scalar case, right, you found that derivatives are also functions. So originally you just computed them as numbers that represented slopes, but of course the number depends on where you are along the curve. Well, in the vector case, the multiple variable case, okay, the Jacobian matrix J is also a function. Of where you are, of the input variable x. It happens to be matrix valued. Okay, so here's an example. Here's a function of 3 variables with 3 components. Right? So if you like, we could write out what f1, f2, and f3 are. Okay, so we can do our Jacobian by definition. So first we take the derivative of f1 with respect to x1. So that gives me x3 squared. Remember, with partial derivatives, whatever variables you're not differentiating with respect to are treated as though they're constants. So df1 dx1, the first term is x3 squared. The second term, so again, just think of this like e to the 2x1, right? So that would bring the 2 down. So in this case, the constant is x2, e to the x1, x2. So all that is just one entry of the Jacobian matrix. Okay, first row, second column is df1 dx2. So that gives us negative x1, e to the x1, x2. First row, third column, that's df1 dx3. That gives us 2x1, x3. Okay, second row, first column, that's df2 dx1, which is 0. Second row, second column is df2 dx2, 1. Okay, second row, third column, df2 dx3. All right, and then third row, first column is df3 dx1. Then we have df3 dx2 and df3 dx3. Okay, so 3 variables, that means we get a 3 by 3 matrix. It's not a constant matrix, right? This matrix is itself a variable, function of x. So just to drive that home, we could evaluate j of 0, negative 1, 1. And this is just going to be a numerical 3 by 3 matrix. So we get 1 plus e to the 0. We get 0 because of the x1 here. We get 0 here. 0, 1, 1. X2 times x3, x1 times x3, x1 times x2. Okay. So now, how do we use the Jacobian? So once again, we have our linearization. So f of x, here is the linear part. That's the linearization of f at the point A, which is a point in n-dimensional space. The big O term is just showing us that errors are quadratic when measured in the norm. So again, this just shows that it's valid for x close to the point of linearization. When x is close to a, that term is small. So, with all these tools now, we can go back and repeat the fixed point analysis we did in one dimension. So here's our fixed point iteration. Where G is a map from Rn to Rn. Okay, that defines a sequence of iterates, a sequence of approximations to a fixed point. If R is an actual fixed point, then we can define the errors as the difference between the x's and the r. Okay, so that error sequence, then, if I take the fixed point iteration equation and subtract r from both sides, I get this here, where I've rewritten xn using the formula for en. Okay, but now I linearize the g. So I get a g of r plus the Jacobian times the en plus some higher order terms. But since g of r is equal to r, these two terms cancel out. And what we're left with is just j, the Jacobian, times en. So again, we have that the error vector at the n plus first iteration is j of r, but r is just a fixed value. It's a fixed point, right? So that's just some constant matrix times en. In other words, we just keep multiplying the errors by the Jacobian matrix over and over and over again. That's a power iteration. We know all about the power iteration. We expect that the errors go to 0 if and only if all the eigenvalues of j at the fixed point satisfy that their absolute value is less than 1.